Welcome students to the video lecture series of our online courses. This course is complex analysis with course code MAT 18 R4026. This is unit 1.2 offered by the Department of Mathematics, Kalasalingam Academy of Research and Education. So today's topic is power series. So this is second lecture on power series, and today I will be covering the concept of radius of convergence of power series. Okay. And I will be also illustrating this concept using some problems. Okay, this is very important, and I will be also describe what we mean by Cauchy-Hadamard theorem. So these are the major aspects of today's video lecture. So this theorem, as you all know from our previous series, okay, that what it says to every power series summation n equal to 0 to infinity a n z to the power n. Okay, this is a power series in Z only. As you know, here ANs are complex numbers, and this is an infinite series. Okay. So for this kind of power series, there corresponds an R. Okay. This capital R is a real number, as it is here. This may be 0, or this may be all the way to infinity, and it may be any other finite real number also. So let me take a highlighter. Sorry. Okay, here I got it. Yes. So I was describing this theorem. So every power series in Z corresponds a real number R. This real number may be 0 or any finite real number, or it may be all the way to infinity also, for which the series, this series, converges absolutely in modulus of Z less than R. Okay. If R is greater than 0, strictly greater than 0, and less or equal to infinity. Okay. So what this means? This simply signifies that for all Z whose modulus is less than R. Okay, so this is basically a circular disk centered at origin with radius R. So in this circular disk, this power series converges. And this convergence is absolute convergence. As you know, absolute convergence means summation of modulus of this, modulus of mod an into z to the power n converges. Okay. Number 2 is saying that converges uniformly in mod z less or equal to some small r less than r. Okay. So this is a compact disk. This circular disk was open, and this is compact. Since it's closed here, it's taking the boundary value small r also, and this small r, it's less than r. So this compact disk modulus of z less or equal to small r actually contained in this open disk mod z less than capital R. So in this compact disk, which contains in this bigger open disk, the this power series converges uniformly. I have already described in our previous lecture what we mean by uniform convergence of a power series. And last, it diverges whenever mod z is greater than R. For any this time R may contains R may be equal to 0, but it cannot be equal to infinity, since the region, there is no region outside infinity. So all the modulus of complex number has to lie in this limit only. That's it may be either 0 or less than infinity. Okay, so it cannot cross infinity with modulus of z. Okay. This is not possible, and this is also not possible anywhere in our mathematics. So infinity is the largest thing you can achieve. Okay. So what it says that this power series diverges outside of this open disk, open circular disk. Okay, since here we are considering mod z is greater than r, so if we consider the circle centered at origin with radius capital R, then outside of this circle, this power series diverges. So this R is a very important quantity for any power series. Okay. Any power series, this R is very important quantity. It basically gives a circular disk to you in which the power series converges, and out of which, out of the circular disk, this power series diverges. And this R is known as radius of convergence. In short, we sometimes say it as ROC. ROC, ROC stands for radius of convergence. Okay, so let's go to the next slide. So here, what do we have? We have a famous theorem by Cauchy-Hadamard. This is to describe or to find out the value of ROC for any given power series in this form. Okay, so the theorem statement goes like that: the power series summation n equal to 0 to infinity a n z to the power n has radius of convergence capital R, where 1 by R equal to limit supremum n tends to infinity modulus of a n whole to the power 1 by n. Here we observe that the convention 1 by 0 equal to infinity and 1 by infinity equal to 0. Okay, so this also admissible, this two operation. We can take it as and this is nothing but extended real field. So in the extended real number field, these two operations basically assumed. So what it gives ultimately? It gives ultimately the value R for any given power series in this form. Okay, so there is small proof for this. I will just like to describe. For any point z not equal to 0, we have limit n tends to infinity supremum of modulus of a n z not whole to the power n whole to the power 1 by n. This can be written this form: limit sup n tends to infinity modulus of a n whole to the power 1 by n z naught. Okay, so this is nothing but 1 by r into z naught. According to this expression, 1 by r is this. Okay, and this always exists. The existence of this limit can be verified from your differential calculus knowledge or series sequence knowledge also. Okay, so you can do it by your own. The concept of series and sequence, especially sequence here, you can show that this limit always exists, and the value of this limit we are putting it as 1 by r. So that's why it is 1 by r into z naught. So according to the previous theorem, where we have found the existence of R, what we get? The series summation n equal to 0 to infinity a n z naught to the power n converges absolutely when mod z naught is less than R, and diverges when mod z naught is greater than R. This is true from this statement. Okay. Converges absolutely whenever mod z less than R, and diverges when mod z. So we are using this here. So in view of the above theorem, the radius of convergence is capital R. Now, when R equal to infinity, if you find that this R is infinity, then what does it mean? The series converges everywhere. Okay, so at the whole complex plane, the series converges. This is true for power series like of e to the power j. That's the power series is given by, in this case, 1 plus z by 1 factorial, z square by 2 factorial, dot, 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 dot. So we know this power series converges to e to the power n, and this convergence hold for any complex number. Okay, so in this case, the radius of convergence will be infinity. And when r equal to 0, the series converges only at z equal to 0. Okay, so this is quite obvious from this expression that if you put z equal to 0, then this is nothing, each and every term will be 0. So for z equal to 0, power series always converges. And for this case, we will say that radius of, if it is only converges at z equal to 0, which is trivial basically, then we will say r equal to 0. Okay. Okay. So from this result, we can also set up these two corollary. This two formula also gives radius of convergence. So what it states the radius of convergence r of the power series this is determined by a 1 by r equal to limit n tends to infinity modulus of a n whole to the power n. Okay. So here it is written the supremum. We have simply omitted supremum here. Whenever this exists, that means this must exist. Sorry, this limit must exist. This limit always exists. Okay. And whenever this exists, both supremum and infimum are same. That's why no need to emphasize supremum here. Okay, it exists. And the second formula, what it's 1 by r equal to limit n tends to infinity modulus of a n plus 1 divided by n. So this formula can be applicable only when none of the coefficients of the power series, coefficient means this ans, is 0. Suppose you get some coefficients or at least one coefficient of this power series to be 0, then this division something by this 0 will not be defined. So whenever you are using this formula, make sure that your coefficients are never 0. Okay. So these are the some examples. So consider summation n equal to 1 to infinity a n set to the power n, okay, where this a n is given by this formula 4 into a n equal to n divided by 4n squared plus 1. Then the ratio test. Okay. Ratio test. Okay. Ratio test means this formula, number B. This is ratio test. Okay. Ratio test given by corollary applicable only when a n not equal to 0. For each n, we have modulus of a n plus 1 divided by a n. We calculate this using this given definition of a n. And what we see that this tends to 1 as n tends to infinity. So what is this? This is equal to 1 by r. So 1 by r equal to 1. Therefore, r equal to 1. So the series converges. The radius of convergence equal to 1. So therefore, the series converges for modulus of z less than 1 and diverges for modulus of z greater than 1. Quite obvious. And consider the second example, summation n equal to 0 to infinity 1 by 3 plus I whole to the power n z to the power 3n. Very interesting. So look at the an's here. Basically, this is not an, this is a3n. So whenever n are multiple of 3, it may be 3, 6, 9, 12. So a6, a9, a12, these are defined, and rest others, that is a2, a4, or a5, a7, a8, these are all 0 then. Okay. So only non-zero coefficients are those which are multiple of 3 only. So in this case, you cannot employ ratio test. Okay. That's the note is written there, I guess. Note that the ratio test is not directly applicable. Okay. You cannot apply it directly, but you can transform it. But however, we think of this as series in new variable z cube. So let's change the variable z with z cube. Okay. So simply write w in place of z cube. Then this series can be written in this form: summation n equal to 0 to infinity 1 by 3 plus I whole to the power n omega to the power n. Sorry, w to the power n. So this is now the new power series in the variable w. But look at here. For this case, there is no zero coefficient here. Okay, no zero coefficient here. So now we are in a position to use ratio test. So our ratio test gives 1 by r equal to limit n tends to infinity modulus of a n plus 1 divided by a n. After putting the values of an and an plus 1, this is what we are getting here. And finally, the limit gives 1 by root over of 10. So from this equation, 1 by r equal to 1 by root 10, we are getting r equal to root over of 10. Now, this is the radius of convergence for this power series in W. Now, the question was to find out radius of convergence for this power series, which was in Z. So there is a relation between W and Z. So we will be using this relation only. And so the new series converges whenever modulus of Z is root over of 10 and diverges on modulus of W greater than root over of 10. This is equivalent to saying that the original series converges for modulus of Z root over of 10 to the power 1 by 6. This is we are getting from this relation only, okay? And diverges for modulus of Z greater than 10 to the power 1 by 6. Now, some more example. Okay, consider this power series Z in cube. Okay, n plus 1 divided by n factorial into Z n cube. Again, the ratio test is not applicable since this power series contains so many zero coefficients. Okay, but we may fix Z not equal to 0 and let an to be n plus 1 divided by n factorial Z to the power n cube. So this total term is taken as an here. Okay, this total term, the coefficient into the variable, we have chosen it as an. Now we are employing so this is not equal to 0 whenever Z not equal to 0. That is quite obvious. Now we are employing this ratio test, and what we are finding, the limit value is this, which is less than 1 provided modulus of Z greater than, showing the given series converges only for mod Z less than 1 and diverges when mod Z greater than 1. So this is another technique. When you cannot employ a ratio test directly, you can use this technique also. Finally, let us consider this power series n equal to 0 an to Z to the power n, where your ans, the coefficients are defined this way: I into 3 to the power n when n is given, and minus 3 to the power n for n odd. Okay. So in this case, you can directly find out modulus of n whole to the power n, since the construction of n is very easy to the power n. So you can just simply take mod and take 1 by n, that is nth probability. That will give you 2 for even n's and 3 for odd n's. So this what we this is what we're saying, that this value an's modulus of an 1 by n oscillates finitely. Now we can think of the Cauchy-Hadamard formula. Okay, so this is oscillates, this sequence modulus of an whole to the power n oscillates between 2 and 3. So among 2 and 3, supremum is 3, right? So limit supremum of this sequence, that is modulus of an whole to the power 1 by n, has to be 3 only. So according to the Cauchy-Hadamard formula, 1 by r will be limit n tends to infinity supremum modulus of an whole to the power 1 by n, which is equal to 3. From this equation, you will get r equal to 1 by 3. So this is a very nice example where you can employ Cauchy-Hadamard theorem directly. And therefore, finally, we conclude the series converges for modulus of Z less than 1 by 3 and diverges whenever modulus of Z is greater than 1 by 3. So this is how we solve and find radius of convergence using Cauchy-Hadamard theorem, and two corollaries, obviously. One is ratio test. And I want you to follow some more problems from any standard problem books, exercise books. For your reference, you can also follow the book given into the reference for this course. Okay, so with that, I stop today's lecture, and please follow the next session also. Thank you, students.